The last topic in acid-base chemistry comes from textbooks section 1511 and 1512, and it presents the most recent and broadest definition of acids and bases. These are called Lewis acids and Lewis bases, named for G.N. Lewis, one of America's great chemists who spent his career at the University of California, Berkeley. Lewis's definition for an acid and a base again works on this donor-acceptor, but without thinking about protons. The definition of a base is a substance that donates a lone pair of electrons. So hydroxide is clearly a base, and when it reacts with a proton, it donates its lone pair. A Lewis acid is any species that accepts a lone pair. And so this very traditional reaction of proton and hydroxide form water is a Bronsted-Lowry idea of donating a proton and accepting a proton, but Lewis's definition also classifies proton attached to hydroxide as an acid-base reaction. The Lewis acid base is a larger definition because we can consider compounds like boron trifluoride reacting with ammonia, and in this case the lone pair of ammonia is donated to the empty p orbital of boron to form the Lewis acid-base complex, and in this case the species that accepts the lone pair is the acid, and the species that donates the lone pair is the base. Nothing changes. Anything that's a base in Bronsted-Lowry remains a base in Lewis acid-base theory, but we can clearly see that no protons have been transferred, yet we can still think of this as being an acid combining with a base. So there don't have to be protons exchanged in Lewis acid-base theory. Very often metal cations, when added to water, lower the pH. They're behaving as acids, and Lewis describes this process in a nice way. Let's examine ions, highly charged metal ions in solution. We'll start with aluminum cation, and the 3+ charge means the species is ready to accept electrons, and water has lone pairs that can donate, and so there's a lone pair donor and a lone pair acceptor. What this looks like when we put aluminum ions into water, they don't stay aluminum ions. They react very strongly to form this water adduct, where the lone pair on water is attached to the metal center of the cation, and 6 waters coordinate around the aluminum ion to form a solvated aluminum cation. What happens is we can focus on one of these water groups. When placed into water, we find that they are able to donate protons. So any one of these waters is able to donate a proton and have a hydroxide group now attached to aluminum. This makes the overall charge +2 for the solvated aluminum, and a proton is now floating around in water. We can measure the Ka by doing products over reactants, and we see a Ka 1.3 times 10 to the -5 that is very similar to weak acids that we have been studying. In this last chapter 15 lecture, we also want to look at species in their oxide form, because in nature so many compounds comes as oxide. The alkali metal and the alkaline earth metals have been highlighted, and when we find these metals in the ground, they're often these minerals, they come as oxides, and it turns out that metal oxides act as bases. So if I take the metal oxide, sodium oxide, and we put it into water, we find that it forms sodium hydroxide, which clearly would be a basic solution. And all metal oxides into water do that. The nonmetal oxides, an example of that would be carbon dioxide. When they combine with water, they form acids, and so carbon dioxide dissolves into water and forms carbonic acid. All of the acids that we have looked at so far, any of the oxo acids, have a conjugate nonmetal oxide that can produce it. Nitric acid is in fact can be produced from adding water to N2O5 that adds 1 oxygen and 2 hydrogens and forms 2 nitric acid compounds. So any of the oxo acids, if you remove water, the species you form is a nonmetal oxide that is called an acid anhydride. Anhydride means without water. Let's examine the reactions that the metal oxide bases and nonmetal oxide acids can undergo. So metal oxides act as bases. That means they can be neutralized by acids. So I'm taking the metal oxide, calcium oxide, this is essentially marble, and reacting with the strong acid HCl. And as you know, acid plus base forms salt and water. The salt that forms would be the metal and the nonmetal, calcium chloride and water. In order to have 2 hydrogens and 2 chlorines, we of course have 2 HCl, and statues over time are subject to dissolving, the marble in statues, because that is a basic mineral that will be neutralized by acid in the environment. Let's do one more. We'll take the metal oxide, potassium oxide, and this time a weak acid, carbonic acid, but again you're just going to form a salt and water. The salt would be potassium carbonate, and then water remains. We have examined 2 nonmetal oxides so far, carbon dioxide and dinitrogen pentoxide. Here are 2 more, and I want to focus on SO3 because it's environmentally very important. So SO3, when combined with water, so you just add an oxygen and 2 hydrogens, forms the acid H2SO4. So any acid that we have seen, in any oxo acid that we have seen, you can remove water and form what's known as the acid anhydride, but it is just a non-metal oxide. And unfortunately, we release SO3 into the atmosphere from burning coal. Just the water droplets in clouds converts that to sulfuric acid, and North America has seen great damage to the forest because the rainwater pH can be very low in industrial areas that burn a lot of coal. So let's look at the neutralization reaction of a nonmetal oxide. I'm picking carbon dioxide because it's so prevalent in the atmosphere, but reacting with sodium hydroxide, again, we're acid plus base, this pattern should become familiar, forms salt and water. So we form the water, and the salt that forms will be sodium carbonate. And in order to balance this, I would have to have 2 sodium hydroxides to neutralize 1 carbonate. So we're converting a strong base into a salt that acts as a weak base. The last example is back to Lewis acid-base theory, but in the reaction of CO2 with water. That is handled very nicely by thinking about lone pair acceptance and lone pair donation. So carbon dioxide reacting with water, water has lone pairs, and when they donate them to carbon, this is acting as, the water is acting as a base, carbon accepting the lone pair is acting as an acid. When it accepts the lone pair, it forms a bond. Carbon can only form 4 bonds, so the electrons in one of the electrons pair in the double bond moves onto the oxygen exclusively, and then we can see another lone pair on oxygen donating, and hydrogen moving to accept the ions, and we end up with carbonic acid. So the reaction of CO2 with water is nicely described by Lewis acid-base theory and moving electrons as Lewis bases onto acceptors, Lewis acid.